In this lecture, we're going to look at thin film interference, and you'll notice that this soap bubble has many different colors, has the greens and the reds and the violets, and you see the different colors because of constructive and destructive interference of white light. And we're going to look at how this constructive and destructive interference in a thin film acts and why we see these various colors. Here is a view of light coming in, incident light coming in, traveling in the air, hitting a thin film, in this case of gasoline, and the gasoline is floating on top of water. And so what you have here is light coming in, reflecting off the gasoline to the person's eye. This is ray number 1. But you have partial reflection, but you also have partial transmission of the light traveling down and bouncing off the water. And yes, some light does keep traveling through the water, but we're not concerned with that at this point. This light bounces off the water interface, comes up, and refracts towards the eye as well. And these rays have been separated, but when they are on top of each other, this ray, ray 1 and ray 2, can interfere with each other constructively or destructively for different various colors of light. So if we read this, if we read the left-hand column here, it says because of reflection and refraction, two light waves are represented by rays 1 and 2. They enter the eye when light shines on a thin film of gasoline floating on a thick layer of water. So this incident light comes in, you have reflected ray, the part of the ray refracts and then reflects down here, and then you have some kind of constructive or destructive interference at this point up here that we will see. In order to understand what's going on, we have to understand how waves reflect off of boundaries. When a wave on a string reflects from a more rigid medium, the wave undergoes a phase change. In other words, it goes from a crest here, and then when it bounces off, it comes out as a trough. In this case, the wall is a less rigid medium, so the reflection is upright. If this wall is less rigid than the medium out here, the wave comes in as a crest, goes out as a crest. This is important to remember to understand thin film interference. These two ideas of reflection are very important when studying thin film interference. The relative values of the index of refraction of the materials lets you know if the material the light is entering is more or less rigid. So if the index of refraction is a higher value that you're going into, then it's a more rigid medium. If the index of refraction that the wave is going into is lower, then it's a less rigid medium. So what I would like you to do is look at these three reflection examples, and I would like you to tell me in this section here, pause the video, and in each reflection that occurs, I need you to decide if it's going to, if the wave is going to invert or stay upright. So wherever you see reflection, for example, here and here are reflections. Here and here, here and here. So pause the video and decide if this right here is, will that change the, will that invert the wave or not? Okay, so since you're going from a 1.5 to a 1.4 index refraction, the wave actually stays in phase. It does not invert. And same thing down here, when you go from a 1.4 to a 1.3, the wave stays in phase. So for example, if a crest comes in on this boundary, it reflects back out as a crest. If you go to the middle one, it's same exact idea. You're going from a 1.5 index refraction to a 1.3 index refraction. It's no phase change. Comes in as a crest, comes out as a crest. But if you look down here, the 1.3 to 1.4, there will be a phase change. It comes in as a crest, it'll come out as a trough. There'll be a 180-degree phase change. So here, in these reflections, in both of these reflections, you'll see a phase change because you have low index refraction going into a high index refraction, lower index refraction going into a high index refraction. There's a phase change at both of these boundaries. So what happens here? 1.4 is less rigid than 1.5, so the reflected ray is in phase. It's a crest and a crest. And 1.3 is less rigid than 1.4, so the reflected ray is in phase. Now, one of the things that we calculate all the time is we want to find the thickness of film for destructive interference. So what you have to understand is, if it's coming in as a crest, it'll come out as a crest. You'll see the crest right there. because you're going from a high index refraction to a lower index refraction. And since you want destructive interference, this wave right here coming back up is a trough. Why you want this to be a trough right here? Because you want this crest and this trough to interfere destructively. So you have to think about, well, what thickness does this film have to be to go from a crest to a trough? You have to go back down and back up, crest to trough. So think about what that thickness of film has to be. So in order for a trough to occur, thickness of the film will be a quarter of a wavelength. In order to have destructive interference, because down here there's no phase change. There's no phase change up here. So anyway, you're going from a crest. You have a crest right here coming down and going to a trough. So it's a quarter wavelength down, quarter wavelength up. That's a total distance traveled of half a wave, and that's what a crest to a trough is, a half a wave. Now, in order to go from the crest to a trough, the total distance traveled is that half wavelength. So quarter wavelength down, quarter wavelength up, half a wave. So again, we see here that the thickness of that film, the thickness of this film right here, is 1/4 wavelength for destructive interference to occur. Think about what you would want for constructive interference. If you wanted this to be a crest instead, you go from a crest all the way down to another crest. So that means you would go half a wavelength, then another half wavelength to get to the next crest. So the thickness of this film for constructive interference would be half a wavelength. And so that's what this next section says, is that constructive interference, we'll want a crest to meet a crest, therefore the light has to travel a full wavelength. Thickness of the film is 1/2 wavelength. So in summary, when you have this situation where you have index of refraction going from higher to lower to even lower, you would get destructive interference to be a quarter wavelength for the thickness of the film. And if you want constructive interference, the thickness of the film would be half a wavelength. And what's interesting is that this would actually occur if you went in reverse. If you went from low to higher index refraction, you would have the exact same equations here. Now let's take into account some situations that actually have a phase change. So here's one. We go 1.5, 1.3 to 1.4. Now what you have here is no phase change, so you'll see a crest come in, a crest will come out. Here though, you'll have a phase change. This is where you have a lower index refraction sandwiched in between two higher indexes of refraction. So this is the pattern you'll see for that situation. So if you want destructive interference, where you want a trough to come and be at this position to interfere destructively with the crest, you have to realize that there's no phase change here, so you're just going from a crest to the trough, and so the thickness of the film is going to be half a wavelength. Whoa. The reason why it's half a wavelength is because you want a trough to be here at this position. And since there's a phase change here, you have to realize that when you go from a crest to a trough, it's half a wavelength, but then the phase change causes it to add on another half wavelength, so that's a total of 1 wavelength. So this has to be half wavelength down, half wavelength up to go from that crest to the trough, including the phase change. So you'll see for destructive interference, the thickness of the film is half a wavelength. Now for constructive interference, it's the opposite. It's a quarter wavelength of the film. And you can see, since you want a crest right here, you go from a crest to a crest. That's typically 1 full wavelength, but you can subtract off the phase change here and have it only be a half a wavelength long. And so that's why it's a quarter wavelength down and a quarter wavelength up. So whenever you sandwich in between a lower index refraction in between two higher indices of refraction, this is the pattern that you follow. These are the equations you look at. What's interesting is this also holds true if you have a higher index refraction sandwiched in between two lower indexes of refraction. The same pattern occurs for destructive or constructive interference. So here's that situation I talked about earlier. When you're going from low to higher, you follow that same pattern that we originally saw. Low index refraction to higher index refraction, even higher. That's the exact same pattern as when you went from high to lower. So So you just remember, you don't have to memorize this situation. Just remember that if the index refractions are increasing, you have this situation. Or if they're decreasing, you have this situation. Now you'll notice that these thicknesses say a quarter wavelength in the film or a half a wavelength in the film. How do you calculate the wavelength in the film if you only know the wavelength in the vacuum? That's typically what happens in our problems. We know the wavelength in the vacuum. So let's go ahead and take a look at that equation. What you can do is look at N equals C over V, and you can then look at this as being C divided by F and V divided by F. Whatever you do at the top, you have to do the bottom. So I take that C up there, divided by the frequency, take the velocity in the substance, divide by the frequency, and we know that velocity divided by frequency is wavelength. So we see that the index refraction equals wavelength in the vacuum divided by wavelength in the film. So if you change that around, you get wavelength in the film equals the wavelength in the vacuum divided by the index of refraction. So that's a good equation to write down as well. Now the other interesting point to look at here is that this is the minimum thickness. This is the minimum non-zero thickness. But if you want to get to the next thickness, you have to add a half wavelength onto this. In other words, 3/4 of a wavelength, and then 5/4 of a wavelength, and 7/4 of a wavelength. And down here, if you want to know what the other thicknesses of film that constructive interference would be, again, you add a half wavelength onto it. So you go half a wavelength to 1 wavelength to 1.5 to 2 wavelengths. This is exactly the same idea as when we saw waves resonating in tubes or waves having standing waves on strings. You would always, when you went from one fundamental frequency, when you went from one harmonic to the next, you would have to increase by half a wavelength. This is the same case here. To go from one thickness to the next thickness, you add on half a wavelength. So this is how you find the constructive and destructive interference patterns of thin films, and how you calculate the thickness of the films. There's an interesting experiment that occurred at the beginning of the 20th century, the Michelson-Morley experiment. This experiment here looks something like this. What happened was there's this thin film coating that they used to allow for constructive and destructive interference due to reflection occur. And this used the idea of thin films. You also will know thin films. You also will see thin films on lenses for photographers. And there's many applications for thin films in industry today.